It's not like you have test tomorrow.
Yeah.
Halloween, yeah.
Don't worry, I'm gonna be taking fun.
Maybe just all
We're
that.
gonna text you today. Okay.
I agree. Well, wait, so.
All right, so we're going to just basically build off of what we've been doing before. Not anything new, it's just the problems are gonna get a little bit longer. The common denominator, steps can feel a little messier, but really, it's the same idea where we're just trying to use different strategies to try to get our left side to eventually work towards looking like the right side. And once we're able to get that beginning to end, then we know we've ended the problem. We're able to stop the problem if we're able to step by step show the work that will lead us from the left side to the right side. So the big things are using trig identities, common denominators to try to push two fractions together, converting everything in terms of sine and cosine. But depending on the problem, we may not be doing the same steps for every, we may be doing something a little bit differently, just depending on what the problem gives us, and we're just adapting to what the problem gives us and trying to step by step move closer towards the right side. So we'll have another day to kind of build on this tomorrow. Wednesday, we'll do review. Thursday, quiz just over these identities. Yeah, so, and then we're gonna start trig identities on Friday, or some of the different identities on Friday, and we'll talk about that when we get there. So, okay, so if you need an extra sheet, feel free to grab one. I do feel like these problems may need a bit more space than what I provided for you. So I'll be working on a separate sheet as well. Okay, so if you guys can turn to page 9. Okay, so one thing that I see is, well, we're always going to start on the left side and trying to move our way towards the right side. And one thing that I see is the left side, we start off with secant x plus 1 over tangent x. The right side, our end result will be in terms of sine and cosine. So that kind of gives me a hint that, okay, eventually I have to get everything in terms of sine and cosine. So I'm just going to go ahead and take care of that now. But okay, so what can we do with secant? Secant can turn into 1 over cosine plus 1 all over. And tangent x can turn into all right, so we have everything in terms of sine and cosine, but we're still a ways off to get to that right side. So we know that this is a little messy because you got a fraction within a fraction. So here's our strategy here is, well, if I can get this numerator to be just one single fraction, then a fraction divided by a fraction is a lot easier to work from than what's given here. So I'm going to kind of step to the side here and just focus on trying to clean this up. If I can get this to be one fraction, then I can have a much easier time working with this this denominator. So if I step to the side here, I want to try to merge this together. So that means I do need to find common denominator. What's my common denominator here? It's cosine x, right? This is really 1/1, so we know 1 can go into cosine. So all right, so now we try to balance our fractions here. Cosine is already cosine, so nothing has changed. Here, my denominator is 1/1. 1/1 is not the same as the denominator cosine x. So what's missing here? Both by cosine. All right, so now we can at least get it to be one fraction. So now this is all over sine x over cosine x. So this is what we've achieved, right? We've gotten it down to one fraction, which will make it a lot easier to merge with that fraction once we multiply by its reciprocal. Okay, so any questions up to this point? We've gone from here to here. A fraction divided by a fraction is the same thing as a fraction multiplied by its reciprocal. Flip this up, sine over cosine can be flipped up to be what? Cosine over sine. All right, are we okay with that? All right, what's nice about lining these two fractions up? Okay. Cosine goes away. We're getting closer, right? We have just one fraction, and it's in terms of sine and cosine, but it's not quite the same as where we want to be. Okay, but we're making progress, right? Close. We're getting closer. All right, so 1 plus cosine x over sine x. I'm not really able to clean this up any further because, right, there's no trig identities for me to use. So what if I think we've seen this before, right? We can kind of make something out of nothing. Is there something that we can introduce into the problem so that we can maybe use a trig identity? Yeah, not times another cosine. Well, if I times the cosine, then I got to deal with cosine plus cosine squared x. Let's deal with that sine, right? That sine is a little bit cleaner, so I'm gonna multiply top and bottom by sine. And we're trying to make something out of nothing here, right? We're trying to get that sine x to produce something that we can kind of jumpstart some identities. But okay, now my numerator, I don't want to distribute that through, okay? Because that 1 plus cosine x, we're hoping will kind of work itself out in terms of maybe reducing. The reason why is because I haven't changed anything yet, because if I multiply by sine x over sine x, what's sine x over sine x? That's the same thing as what? Multiplying by what? By 1. If I multiply something by 1, I haven't changed anything, right? So why am I doing this? Because I want that denominator to show me something that I can work with. Because I know I still got to create different versions of this problem because I'm not able to get to where I need to be just with this form alone, right? So I'm kind of introducing something into the problem so I can involve that sine squared. And what's nice about that sine squared? We have an identity, right? We can get that sine squared to be equal to what? 1 minus cosine squared. Okay, so let me just pause for a moment here. Any other questions about why we're doing this and how we got there? Okay, because we're trying to, this is as clean as it gets. We can't cancel, reduce, so we're kind of introducing something into the problem to force some other properties to allow us to change our problem or change the form of the problem. Okay, so sine squared x, we said, is the same thing as 1 minus what? right? Because I'm just using this trig identity here, subtracting cosine squared. Sine squared equals 1 minus cosine squared. Okay, I think we've seen this before, right? That denominator, we can do what with this? Factor, right? Difference of squares, right? Those are both perfect squares. A squared minus b squared equals a plus b times a minus b. 1 breaks down into 1 and 1. Cosine squared x breaks down into cosine x, cosine x. Doesn't matter what order you put the signs, but we do need 1 positive and 1 minus. All right. What do you see? Bounce. Are we at the end? Sine x over 1 minus cosine x. Sine x over 1 minus cosine x. That matches. We're good. All right, we're starting with the left side here. Is there anything that seems obvious as to what we can do as our first step? Yeah, let's just get this, let's just get some tangents to show up, right? We know that cotangent is reciprocal of tangent, so at least we can get tangent to show up. It may not match exactly the form, but at least we have the trig function that we want to work with, right? Right, I have my tangent showing up, but these are messy complex fractions. So guess what we need to do for both the top and the bottom? Ideally, we want to merge the two together. So if I want to merge those two terms together, I need to find what? Common denominator, right? Okay. So I got to do for both of these. Looks like both of them is needing it. So it looks like my obvious denominator is tangent of v. Any adjustments needed here? Well, do I need to do anything for tangent v to tangent v? No, so I can just, no balancing needed. But this one is different, right? This denominator is 1, so I need to multiply the top by what? Tangent v, right? Okay, is everybody good with common denominator and just trying to get those, identifying the common denominator and then balancing out the fractions? Okay, we'll clean that up later. I can do the same or similar steps as this bottom part, right? Okay, any balancing needed here? This we're good, right? Down to 1. How about from 1 to tangent v? I need to and multiply by 1, right? Because really, this is really showing 1 over 1, which is not the same denominator. So it takes me 1 times tangent v to get the tangent v. So I need to multiply the top by what I did to the bottom. All right, so now that we have common denominators, we can merge the two fractions or merge each individual fractions together. So this top becomes what? What does that become once I put it together as one fraction? All over tangent v, yeah. Same thing here at the bottom. 1 plus tangent v Right, so the nice thing is we have nice, clean, I mean, still a complex fraction, but at least it's just one fraction divided by another fraction, right? We're not trying to deal with the multiple terms. It makes it messier here, but now this feels a little bit cleaner because now I can multiply the top by what? By the, yep, your circle at the bottom, right? Okay, so I'm gonna step next. So my reciprocal is tangent v over 1 plus tangent v. All right, what do you see here? Tangent v, tangent v. Okay, did we get there to the end? Does it match? Yeah. Okay, number 3. All right, does anybody still need to look at number 2? Okay, here's number 3. Okay, any ideas as to what we can maybe do as our first step? Mhm. Okay. Yes. Now, if some of us may be thinking, well, if I turn to sine and cosine, then that tangent is not going to be there anymore. Then how am I going to get that tangent to show up? That we can handle later. Okay. But what's our eventual goal if we were to get that in terms of sine over cosine? What's going to be nice about that step if we were to do that? Yeah, so the idea is common denominator. I know that we don't see a denominator over on the right side, but at least we see the right side is one term, right? I mean, it's multiplied, but it's still considered one connected term here. So if I can at least merge those two together into one fraction, then I can play with the fractions and hopefully use identities to kind of head towards this, right? So it's not going to be a one step to the end. It's more like, okay, I see the connectedness of the right side, and I can get that to work if I can get both sides to show me something little similar, even though it's going to come at the cost of losing that tangent. You know, we feel like, oh, wait, if I lose that tangent, then how am I getting closer to my answer? Not initially, but at least I can merge the two fractions together. So yeah, let's work towards common denominator. All right, so is there a common denominator that we can easily identify between these two fractions? Cosine squared, right? Anytime you see a 1, that's easy. You know that it'll just take on whatever the other denominator is. Because 1 is always small enough to go into the other denominator. Okay, we got a balance. If my denominator looks the same as my original fraction, then I can just carry that down. This is different, so I need to multiply the top by what? Cosine squared, right? If you think about it this way, in order for me to get from 1 to cosine squared, I need to multiply the 1 by cosine squared. So whatever I do to 1 to get to this step, I got to do the same thing for the top to balance it out. So the top is going to now be sine squared cosine squared. Right, so keeping our goal in mind, we have common denominators, so that means we can merge the two fractions together.
The two signs cancel out since they. Wait, never mind.
Oh, you mean these two cosine squared? Is that what
The
you're
two
talking
signs, oh, never mind.
about? Right, but remember this sine squared theta is connected to cosine squared, so we can't, yeah, these aren't like terms, so we kind of have to write them separate. All right, so at least we've gotten it down to one fraction. That's a good start. Anything that we can, any ideas what we could do next? Anything stand out to you? So I'm looking at the numerator and I'm thinking, is there another, what can I do with that? What about factoring? What can we do? Is there a GCF that we can maybe get this to look like something else? What's GCF for the numerator? Sine squared, right? If I look at my two terms here, I want to get it to a different form. Factoring is something that can quickly get us to a variation of the problem that may look a little different for us. So we see that these are both two terms here. They both shared a sine squared, so I can pull a sine squared or divide a sine squared from both of them. Divide, take out a sine squared, or in other words, if I divide by sine squared, what's left? 1. Okay, so 1 minus. And if I take a sine squared from the second expression, what's left? Okay, look at where we are and look at where we want to be. Anything ring a bell here? Okay, good. Now, let me talk about something here. The nice thing about multiplication and division is you can split up, separate, move things around any way you want. Now, you can't quite do that when there's addition and subtraction, but the sine square, the parentheses, the cosine square can kind of be moved around in maybe in a variation that may be more helpful. So let me write it this way here, because what if I did this? What if I split this up into multiple fractions? And I think in terms of, well, this is it the same thing as sine squared theta over cosine squared theta times 1 minus cosine squared theta. Right, so if I think of it, I'm just kind of moving things around. And if I were to move things around, I haven't changed anything. I just try to make it group things a little differently. Yes. We don't, because it's like this. If I have x times y over z, I can break it down into x over z times y. It's not the same thing as if I had x plus y over z. If I have a plus sign in between, if I have a plus up top, I got to split them up into two separate fractions with a common denominator. But anytime things are multiplied, I can just move things around without having to deal with a lot of messiness. Because this is the same thing, right? If I were to put this together, isn't it the same thing as sine squared times 1 minus cosine squared all over cosine squared? So I should be able to make my way from here to here without any trouble, right? Now, what's the advantage of this form here? What do you see sine squared over cosine squared? Yes, question. what happened to the sine squared here? Or in the beginning? This one here? Oh, why did that go away? Okay, so I factored the sine squared out. So when I factor it out, then I'm just left with this, because what if I redistribute this through? Am I able to get back to this point here? So what's sine squared theta times 1? Sine squared. What's sine squared times cosine squared? Sine squared cosine squared. So what I did was I took out a GCF, and when I take out GCF, I'm able to divide by my GCF, and whatever is left over from that process will go inside the parentheses. Yeah.
When did negative be taken in front of like,
Say it again?
so for like the factoring part, that like the.
Okay, right here, yeah.
Wouldn't the negative be in front of the one technically? Because it's like on the, previously before you factored it, the negatives right in front of like the whole term.
Oh, you mean this right here? You mean this is in front of the whole term here? This minus
So
sign,
the numerator, like right before you factor,
right here?
like yeah, that minus sign, wouldn't that be in front of the one when you factor it? So I'm trying to say, it'd be like -1 plus cosine.
Well, this sine squared is with the 1, and the sine squared cosine squared is with this cosine squared. So let me show you a different way here. What if I wrote it this way? Sine squared theta minus sine squared theta cosine squared theta. Okay, so we said the common denominator is sine squared, right? So I'm going to take a sine squared out. So if I take a sine squared out, that means I'm dividing by my GCF. Sorry. I'm dividing by my GCF. And putting the leftover in here. So what's sine squared divided by sine squared? It's 1. So that's why it goes here. And then what's sine squared divided by, what's sine squared over times cosine squared divided by sine squared?
When
Minus
minus,
cosine squared.
that makes sense. Oh, thank you.
So if you're ever unsure about what you did with factoring, whether you did it correct, go back and redistribute, right? If you can redistribute and get back to where you came from, then you know you did your factoring correctly, right? So if you're ever unsure about your factoring, work backwards, right? I should be able to distribute the sine squared through and get back to my starting point. Okay? If I can't, I know something didn't go quite right. Okay, so what do we say here? Sine squared over cosine squared, the same thing as what? Same thing as tangent squared, right? We're always looking to our end result to see if we're any closer. And what's the nice thing about 1 minus cosine squared?
Trig.
Yep, and that's equal to what? Sine squared right here, right? So this is tangent squared. This is sine squared. And then we've reached our end, right? Tangent squared times sine squared, that's what we want. We're just using different methods to try and get the left side to eventually turn into the right side. Okay, number 4. I know, okay, so I know that the tangent doesn't quite look like secant yet, but let's think in terms of getting this to a different form first. Tangent to the 4th plus tangent squared t. Anything that stands out to you as maybe a first step to get this to look like something a little different? What can we do? Yes. We could. There's actually a better method. Yeah, I know it's tough, right? You're looking at this going, well, it looks like sine and cosine could be something that we can do. The nice thing is that these are both tangents. Yeah, factor, right? So if I see something that I can factor, I think that could potentially move our problem a little faster. So what's a GCF that's shared between both tangent 4 and tangent squared? Tangent squared. So I'm going to take a tangent squared from both and put the leftovers inside a series of parentheses or brackets. So I'm going to divide by my GCF and see what's left over. So what's tan 4 divided by tan squared? Just what? Tangent squared. What's tan squared divided by tan squared? All right. Anything nice about this? Tan squared plus 1, right? What's tan squared plus 1? Squared. Secant squared. Yeah. Is there anything we can do with this tangent squared, you think? You can rewrite it, right? Tangent squared is equal to, because if you look, everything we want is in terms of secant, so maybe I can turn both of these in terms of tangent. Sorry, in terms of secant. So tangent squared, I can replace tangent squared with what?
Secant squared
Minus 1, right? We're every step we take, we're just looking to see, okay, what could be my next step to get myself closer to the right side? And I have everything in terms of secant, so what if I just distribute this through? Hopefully I can get to where I want to be. So I'll distribute the secant squared through both of these terms here. Secant squared times secant squared is secant to the fourth. Secant squared times 1 is secant squared. All right, number 5. All right, we're just playing with the left side here. I mean, we really can't cancel anything out. We're almost to where we want to be anyways. So I think we've seen this strategy before, right? What can we do to maybe get something started here? Maybe we can use a trig identity to create a different version of this problem. Or is there maybe something that we can introduce into the problem to force a trig identity? I'm sign. Right. So anytime I want to try to get a trig identity going, then I can always pick out something that looks easy to turn into. Sine squared theta can be turned into minus cosine squared. Difference of squares. Reduce, reduce, and we should be at the end. Mhm. Okay, take a look at number 6. What do you think is the first step that you would take? Yeah, good. Let's find common denominator. Especially if I see multiple terms added or subtracted, and there's only one term on the right side. My first goal is maybe not. I don't need everything in terms of cosecant yet. Let me just get the two fractions to be together, and then I can within the fraction I can then play with the numerator and denominator. Let's get the foundation set first. So the question is, what is the common denominator? If you see two denominators that are completely different, then we need both of them to create the common denominator, right? All right, so now we got to work on balancing each fraction's numerator. All right, look at your old denominator versus your new denominator. What is different? What do I need to add? Yep, by sine t, right? Because this 1 plus cosine t is missing a sine t to get to here. So whatever is missing between my old and my new denominator is what I need to make up the difference with the top. Okay. So what's sine t times sine t? Sine squared. All right, what's missing between here and here? 1 plus cosine, so I need to multiply by 1 plus cosine. All right, I'm sharing a common denominator, but I probably want to FOIL all this out to see what comes of it, right? Because I don't want to leave that instead of parentheses. I want to try to get the numerators to clean up a little better. So I'm going to FOIL all this out here. So I'm going to put the steps here. Just 1 plus cosine t plus cosine t plus cosine squared t. I'm just going to merge this together here. The nice thing is, once we get it down to one fraction, then we can kind of just work on one side at a time and kind of piece by piece try to move, see if we're getting any closer towards the right side. All right, so the numerator here, anything that we can do? Any identities that you see? Yeah. What about sine squared? Yeah. Sine squared plus cosine squared, right? If I have multiple terms up top and they're add or subtract, I can rearrange it in any order, right? I can put the sine squared plus cosine squared together, and I know that this will just turn into a 1, right? And then 1 plus 1 is 2. 2 plus 2 cosine t. Let me write that here. All right, anything else we can do with the numerator? How about factoring? Okay, GCF, right? We can take out a GCF of 2. So if I divide by 2, what's 2 divided by 2? What's 2 divided by, what's 2 cosine t divided by 2? Plus cosine t. Okay. What's next? Yeah, so. All right, so I'm just left with 2 over sine t. Am I any closer to the end? Sine t in the denominator, same thing as what? A reciprocal of sine is cosecant. So I have my result there. All right, let's do one more here. Number 7. Okay, so you, typically I would say always consider the left side first, but you could start on the right side, move to the left. And that's what I would do here. I find that it's easier to get something more complicated into something that's more familiar. So in this case, I'm going to start on the right side, move to the left. Okay, we just can't work on both sides of the equation, but you can always decide which one you want to work from. Typically, though, I think I'll just write it give you the problem in a way where you're always starting on the left side. But this one, yeah, I'm gonna rewrite it. I find it easier to just start with the more unfamiliar one and work towards the more familiar one. Okay, so what's something obvious that we can start off, begin our problem here? Yeah, let's get that cosine to show up. There's gonna be a whole bunch of complex fractions, but at least we can just get our problem to just show cosine, and we can, piece by piece, kind of get this to look like the right side. All right, so common denominator for the top and the bottom. I need to go through common denominator for both the numerator and denominator. The whole purpose is to get it down to just 2 clean fractions so that we can just multiply by the reciprocal. Okay, dividing by a fraction is the same thing as multiplying by its reciprocal. So I'll do this times the reciprocal of this. What happens here? Cosine goes away. I'm able to reach my goal there. Okay, we'll continue tomorrow. Don't forget your phones. Let me know if you have any questions.
Yes, please.